Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of iterative in-order traversal. This question gives you a binary tree where every node has a value property. In this case, we're going to be dealing with integer values. Every node also has a parent node. So every node does keep track of its parent node. And every node also has both a left and a child node. And these nodes can be either binary tree nodes themselves, or they can be the none or the null value. Now, the question wants you to traverse this binary tree using the in-order traversal method, and it's going to give you a callback method to call on all of the nodes in the tree as you traverse it in order. But it wants you to do so iteratively, as opposed to recursively. So before we dive into the question, it's important to define and to understand what in-order traversal is. And here, of course, if you are unfamiliar with that, I'm 100% going to encourage you to check out the BST traversal question that we have right here on algoexpert.io, because it'll go through in-order traversal and how to implement it recursively, which is the typical way to implement it, as well as a couple of other popular traversal methods for binary trees. But so the way in-order traversal works essentially is for any given binary tree, you traverse all of the left nodes first, then you traverse the sort of top level node, and then all of the right nodes. And typically this is implemented recursively because you can literally write just a few lines of code and the algorithm works. But the caveat there is that because you're using recursion and you're making a bunch of recursive calls, you end up using space because the recursive calls take up space on the call stack. So iteratively, you're actually going to end up using constant space. And so this question can actually be asked a bit differently. Sometimes you'll hear this question asked as follows: traverse a binary tree in order using constant space. And that is literally just another way of saying traverse a binary tree in order iteratively. Now, how do we solve this question, right? The first time you hear the prompt, you tend to think to yourself, okay, this is really easy. I'm just going to go all the way to the left of the tree, and then I'm going to kind of work my way back up. Well, if you start tackling it and dabbling with it for 5 or 10 minutes, you'll quickly realize that it's a lot more complicated than that. There are definitely some nuances and edge cases to watch out for. But once you finally get to the solution and kind of realize the crux or the sort of key thing to realize, it becomes pretty simple to implement in code. But so the key thing to realize that I just mentioned, which definitely might be tricky to come up with, is that when you are traversing a tree, like the one that we have here in front of me, when you are traversing the tree and any given node, let's say we're traversing this node with the value 2, you can either call the callback, right, that you were given on it, or you can not call it and decide to call it at a later time, right? And what is going to make you decide whether or not to call it is basically what the previous node you traversed was. Because think about it. If you are coming from this node, from the node with value 1 to the node with value 2, right? If you're going from here to here, then you know that you should not call the callback on the value 2, right? Because in in-order traversal, you first call the callback, or you first explore all the nodes to the left, then the current sort of top-level node, then all the nodes to the right. So in this case, you would want to first go down here and explore all of this sort of left subtree of the node with value 2. Now, on the other hand, let's erase these arrows. Imagine you had already explored all this left subtree, and you were coming up like this from this 4 node here. Well, then here, you would want to call the callback on 2, because you've explored all of the left subtree of 2, and you've presumably called the callback in all the right places there. And now it's time to call the callback on 2 and to sort of officially traverse it in order. And so that's why you can look at the solution here in the top right corner. By traversing this binary tree in order, we'd first call the callback on 4, which is kind of the leftmost node. Then you'd go to the right, which is 9, then back up to 2, back up to 1, and then you'd go to the right, but first to the leftmost subtree in the right subtree, which is 6, then 3, and then 7. Okay? So the key thing to realize, like I just said, is that to decide whether or not to call the callback on a given node, you have to know what the previous node you had just traversed was. And so that's what we're going to do for this algorithm. We're going to traverse it in some manner, and we're going to keep track at every node what the current node is, what the previous node was, and what the next node is going to be. Okay? And we're going to do all of that iteratively so as to use basically almost no extra space, just a constant amount of space, just a few variables. So what I'm going to do for this video is I'm going to go through this example on this binary tree, which happens to kind of cover all of the nuance and edge cases that you might encounter. And then we'll dive into the code walkthrough and type it out and really make everything clear. So when we first traverse this tree, right, the current node is going to be 1, right? So I'll put, maybe what I'll do is, I'll put, I'll put a little line next to 1 to say that it's the current node. The previous node is going to be none, because there's nothing above our current node. And then the next node is going to be 2, right? Because we're going to go to 2. We're going to go left first, because this is in order traversal. But how do we determine that 2 is the next node? Like, visually here, we know that in order traversal means you have to go left. But algorithmically, how can we tell our computer to know that? How can we tell our algorithm to know that? Well, we can say because our previous node is the none value, because we have no previous node, then we know we must be at the root node, and so we must go left. If we do have a left node, we must go left. And in this case, we do have a left node, so we're going to do just that, right? We're going to grab our current node pointer, which is this purple thing, and put it next to the 2. And then we're going to grab our green pointer, let me twist it, and we're going to put it to the 1, because this is our previous node now, right? The node that we were currently at was 1. Now we're moving to 2, and so our previous node is now 1. Okay? And so then we're at 2 now. How do we know that we should not call the callback on 2, and instead we should further explore down to the left? Well, this is exactly the case that I covered 2 minutes ago. We just came from 1. So for us, as humans, we know that because we came from 1, which was above, we have to go down to the left. But what we can tell our computer here, our algorithm, is if the previous tree, because of this green thing, right? If the previous tree or the previous node is equal to our current node's parent node, because remember, every binary tree node here has a pointer to its parent node. If the previous node is our current node's parent, then that means that we just came from the top and we have to further explore down, okay? We have to further explore down. So we go further down. And because we have a left child here, further down, we can just move our current node, boom, to the left child, and we can move our previous node to what our current node was, which is 2. Okay? So now same logic. Where do we go from this 4? Well, what is our previous node? Our previous node is 2, right? This green thing. It happens to be equal to our current node, 4, our current node's parent node, which is 2. So because we know that we just came from our parent node, we have to further explore down. But now you'll notice that there is no left child node here, right? 4 doesn't have a left node. So because it doesn't have a left node, we have hit sort of the bottom of the tree. And now it's going to be time to explore to the right. But before we explore to the right, we have to call the callback on 4. And that's when we call it. So now I'll write in green here, callback on 4. Okay? So we call the callback on 4, and now we go to the right. Okay? We go to the right because after we've called the callback on our current node, it's time to go to the right. Now, if there hadn't been a child on the right node, we would probably do something else, and we'll see that in a second. Like I said, this example kind of covers every case. But here we do have a right node, so we'll move our current node here to the 9, and we'll move our previous node here to the 4. Okay? So now we get to this 9, and the 9 has a parent node, which is 4. 4 is also our previous node. So, at this point, we start to further explore down to the left, right? We see that we have nothing to the left, okay? So we go back up to our current node and we call the callback on our current node. So we'll call callback on 9. And then we're going to try to go to the right. But because we don't have a right node here either, we're going to go back up to our parent node. Okay? And so now our purple thing is going to go back up to the 4, and our green thing is going to go down to the 9, because our current node was 9, so it now becomes our previous node. Okay? So now we're at the 4. What is our previous node? The previous node is 9. Okay? If the previous node had been our parent node, we know what to do, right? When the previous node was our parent node, we would have gone down to the left. We would have tried to explore the left. But now, since the previous node is our right child, right? The previous node is our right child, the 9. We know that we must have explored all of the right subtree, which means that we must have also already called the callback on ourselves, because we always call the callback on ourselves before we go down to the right. So therefore, the next thing we have to explore is our parent node. We have to go back up. Okay? So we're now gonna move our current node here to the 2, and we're gonna move our previous node to the 4. Okay? And so now, because our current node is 2, and because our previous node, 4, happens to be our left child node, we know that we're coming back up from the left, right? We're coming back up from the left, which is exactly that scenario with this arrow that I drew earlier. So because we're coming back up from the left, we're going to call our callback on ourselves. So we're going to call callback of 2, okay? And once we've called callback of 2, we're going to set our new node, our new current node, our next node, to be either our right child or our parent node. Why that? Well, because when we call the callback on ourselves, remember, we always want to go right. If we can't go right because we don't have a right child node, then we go further up. So we're going to grab our current node, move it to the 1, grab our previous node, move it to the 2. So now, again, our previous node is our left child node. So we're going to call the callback on 1, right? So callback of 1. And then we're going to move our current node either to the right or to the top if we didn't have a right node. But here we do have a right node, okay? So we're going to grab this, move it here, and then we're going to grab our 2, move it back to the 1, because that's our previous node. So now now we're back in that very first case at the beginning, which is our previous node, the green thing, is equal to our parent node. So if our previous node is equal to our parent node, remember, that means that we want to explore the left. And because we have a left child here, we're going to grab our current node, move it to the left child, grab our previous node, move it to the 3. Okay? So now 6 is here. Our previous node is our parent node. It's 3. So we look, do we have a left child to further explore? No, we don't. Therefore, we call the callback on 6. We're going to call callback on 6. And then we either check if we have a right child. And if we have a right child, then we go down there. Otherwise, we go back up to the top. Okay? So here, we're gonna go back up to the top. We're gonna move the previous node to 6. Now we're coming back from the left child. So if we come back from the left child, we want to call the callback on ourselves. Let me give myself a bit of space here by moving this here. We're going to call the callback on 3. Okay. And once we call the callback on 3, we either go to the right or we go back up. Since we have a right child, we go to the right. And then we bring this 6 or this previous node to 3. So now we're here. We check what our previous node was. It was 3. It's equal to our parent node. So we want to further explore the left. There's nothing to the left. So we explore ourselves. We call the callback on ourselves. And then we go to the right. Because we don't have anything to our right, we're going to go back up to our parent, right? So because we don't have anything to our right, we go back up to our parent, the 3, put the previous node to the 7. And now remember, now we're at 3, and when our previous node is equal to our right child, that means that we want to just keep going back up, right? So when our previous node is equal to our right child, we keep going back up. So we're going to make, we're going to make our current node be the 1, and our 7 be the 3. Because here you can imagine, if we had, let's say, a node here pointing to 1, we'd want to eventually go back up all the way to that node, right? That's what you have to keep imagining. That's why when we come back from the right child, like when we have an arrow coming back like this, we want to go back up so that we can maybe go back up to parent, right? That we haven't already explored. So that's what we do. And here, because, our previous node is 3, it's equal to our current node's right child node. So we're going to make our current node be our current parent, right? So we're going to move this to be our parent, and we're going to move our previous node to our current node. And now here, we can be done. At any point, this is where in our algorithm, we'll have to specify some kind of, condition. If at any point our current node is equal to none, if we don't have a current node, as in this case, then we can finish. We can stop executing our code, and we are done. We have effectively traversed our tree iteratively. And so this algorithm is going to run in O of n time, because let me erase that and make it clear. Whoops, so it's going to run in O of n time, because at the end of the day, we explore every single node in the tree, and that's pretty much it. And at every node, all we're doing is checking, what was the previous node, what was our current parent, our current trees or our current node's parent. So we're doing these constant time operations. And so the time complexity is going to be O of n, where n is the total number of nodes in the tree. You might be asking, wait a second, but sometimes, we start to climb back up nodes that we've already visited, right? But we're only going to do that at most once. In other words, we'll probably visit a node at most twice or 3 times, right? Like a node like the number 3, we visited 3 times. It so happens that the number 3 we visit 3 times. We visited it once when we went down, then we went to the 6, then back up to the 3 and we called the callback, then down to 7, and then back up to 3, and that's it. So since we'll visit a node at most roughly 3 times, and some of them fewer times, the time complexity is definitely O of n. And the space complexity, surprise, surprise, the space complexity is going to be O of 1, because that's the beauty of doing this iteratively. We don't need to, use up frames on the call stack. We're not doing any recursive calls. We're just going to be storing a few variables and updating them throughout the algorithm. So this is how this algorithm works. It's a really cool one once it clicks. Let's implement it in code so that you can really understand it. All right, so we've got our iterative in-order traversal function defined. It takes in a binary tree as well as a callback method. It doesn't really matter what this callback method is. All we know is that we have to call it on our nodes as we traverse the tree in an in-order fashion. And the first thing we're going to want to do is to initialize our previous node and our current node variables. So the previous node variable is going to be equal to none. Remember, at the beginning, we have no previous node, so we set it to none. And the current node is going to be equal to our tree, the tree that we're given, right? We can assume that we're given the root node of the tree. Now, while the current node is not none, we're going to do stuff. As I mentioned in the conceptual overview, we end the algorithm once we reach a point where our current node is the none value. And that only or the null value, right? And that only happens when the current node, when we get back up to our root node, and then we try to access the parent node of that root node, which is going to be set to none. Okay? And so while the current node is not none, though, we're going to do stuff. The first check that we want to make is if our previous node is either none, right? Or if our previous node is equal to our current node's parent. So if previous node is none, or if previous node is equal to our current node, the parent of our current node, that means that we're kind of coming from the top, and we have to try to explore the left. We have to try to explore the left, okay? So if, in this case, right, in the case that we're coming from the top, our previous node is either none, or in which case we're in the root node, or our previous node is equal to our current node's parent, then if our current node's left child is not none, meaning we have a left child to explore, then we're going to set our next node to be equal to current node dot left. Okay? Otherwise, if we do not have a left node, then that means that we are at the leftmost part of our current sort of subtree. So that means that we have to call the callback on our current node, and we can set the next node to be equal to either the right node, if we have one, or our parent node, right? Because if we have no right node, then we're done. There's nothing else to explore in this subtree. We can just start going back up. So we can say next node is going to be equal to current node dot right if current node dot right is not none, else current node dot parent. Okay, and so here we can use a ternary operator. We could use another if-else statement, but it can get a bit gross. So here, I like to say next node is going to be equal to current node dot right if we have a right child, if the right child is not none. Otherwise, we go back up to current node dot parent. Okay? So that is our first big if statement. If we were coming from the top, this is what we do. Then, what's the second one? Else, if our previous node is equal to our current node's left child, okay? So if we are coming back up from the left, then that means that we must have explored all of the left subtree, if we've done things correctly, and it is now time to call the callback on ourselves. So callback of current node again, okay? And here, we're similarly going to say, in this case, next node is going to be equal to current node dot write if current node dot write is not none, else current node dot parent. So we're going to literally copy paste, like we could copy paste these two lines here, or perhaps we could refactor the code to only have to write this once, though we would have to have kind of nastier if-else statements. But in this case, we're doing the same thing, right? Like basically, when we come back from the left, if our previous node is our current left child, then that means we've explored the entire left subtree, and it's time to call the callback on ourselves and then either go to the right or go back up. And here, similarly, if we ever come from the top, but we don't have a left child, so we hit this else statement, it's the same thing, right? It's time to call the callback on ourselves and then either go right or go back up. And then finally, the last thing here, else. So here, this line 14, this else, could essentially be written as elif previous node is equal to current node dot write, right? That's the last case. The last case is when we're starting to come back up from the right. Let's just write it as an else, because there's no other case, right? So else, and in this case, it's going to be very simple. Next node is going to be equal to current node dot parent. If we're coming from the right, all we have to do is go back up to the parent, and just keep going back up to the parent, until it's time to until we're starting to go back up, or until our previous node becomes a left child, or until we reach none. Okay. And if you remember in the conceptual overview, the example that we had, once we hit this part here on our right subtree, we just kept going back up, back up, back up until our current node was none and we were done. And so now the last thing that we have to do, these are all the if statements in our while loop. But we have to remember that once we've done all this, we have to update the previous tree and the current tree, right? So previous node is going to be equal to current node, and current node is going to be equal to next node. Because remember, all this logic here was all to find which node was our next node, which node was the next node we were going to explore. Also, when were we going to call the callback? And then finally, once we've determined which node is our next node and where we call the callback, well, we update the previous node to be the node that we're currently at, and we update the current node to be the next node that we determined just above. And that is it for the algorithm, right? Once we get out of this while loop, we're done. This method, iterative in-order traversal, doesn't return something, doesn't return a value. It just calls this callback right here. And so this function is going to run in O of n time, where n is the number of nodes in the binary tree. And it's going to run in O of 1 space. And if you're not convinced about the constant space, just look at this code and you'll realize that the only three things we're storing at any given time are previous node, current node, and next node, right? And of course, we can disregard the callback. Like, if the callback is some kind of, fancy function that uses space itself, that's a different story, but we disregard it for here. So the space complexity is going to be O of 1. And the time complexity, as I had mentioned in the conceptual overview, and as I had explained there, is going to be O of n. So with that, I hope that this video was helpful, and I will see you in the next one.